Hey guys, welcome to the tutorial video on Gauss's law for concentric objects. I'm going to have this same intro part for both of the videos, so if you're going to watch them both back to back, then that means go ahead and skip like the first 2 minutes, minute and a half of the second one that you observe. Alright, now the reason I have this intro part is because I'm going to be able to say this sort of two things that are going to stick for both of the types of systems you're going to look at. One system is going to be concentric spheres. The other possibility is concentric cylinders. But for both of them, we can always say a couple of things. Number one, let's go ahead and draw something here. Let's say that's a sphere, or maybe actually we could be just looking down the end of a couple of concentric cylinders. I don't know. It's not important. Alright, first thing is that if you want to find, say, the electric field in here somewhere, or maybe you want to find the electric field out here somewhere, the object around your central object is actually completely irrelevant to what you're doing. It doesn't even matter. Because for Gauss's law, all that actually matters, if you recall, is what is inside of your Gaussian surface. So if there's stuff outside of it, it's irrelevant to what you're doing. Alright, the second thing that we can always say in general is that if this middle object has, say, a charge Q, then the inside surface of the outer object, assuming that it's a conductor, is going to have a charge of minus Q on it. I swear that's a Q. That's really a Q. Honest, I promise. There we go. Now it looks like a Q. Alright, that's, again, assuming that it's a conductor, right? Remember, the idea is electrons are attracted inwards towards the charge in the middle here. Okay, so they migrate in. So if this is a positive charge in here, then you get negative charge accumulating on the inside surface of the outer conductor. Alright, for the outer surface of the conductor, it's going to be whatever it needs to be in order that the inside surface and the outside surface add up to the total charge. So if you're looking at Q inside plus Q outside, they're going to equal the charge on the let's call it the conductor. Which, remember, the way I'm doing this, that's always going to be the outer object. Okay. Now, we're going to have to apply these in specific circumstances, but these are a couple of rules that we can generalize. Let's go ahead and consider the case of concentric spheres. So I made a little video that I'm inserting here, and I'm going to voice over it as necessary. If you would like to follow along with the problem, you can obviously see the text on the screen, but I have also made it available on the Google Drive. So you can get to the text for this problem and for the other video on the Google Drive. Alright, so the first part of the question there is, setting it up, describing what the system looks like. You got a couple of spheres, right? One with a radius of r, right? There it is. Whoa. Radius of r. That's the one in the middle. Alright, it's got a charge Q, and then the other one, it specifies its inner and outer radius, as you can see, 3r and 5r. And for the first, I skipped part A in the video for the moment. I'm going to come back and answer it. But part B, where you're supposed to find the electric field first at r over 2, that's inside the inner object. So what you're going to see me do here is the same derivation that you see in example 15 for the notes, where I'm going to use Gauss's law. Right, there it is, Gauss's law. We're plugging in rho v because we're told that it's an insulator. Okay. Since it's spheres, remember that's that thing where you've got to plug in Q over V for rho. Q is given in the prompt, so you can't leave rho in the answer. You have to plug in Q over V because you have to answer in terms of the things that are given. Alright? And we'll let it play a little more. I make a couple of errors here. That's alright, I'll talk about them. Alright. V enclosed. That's always the volume inside of the Gaussian surface. So that's that bit right there. Okay, so that's my V enclosed that you saw, which is going to be in terms of little r. Remember, the convention is big R is always like the radius of the real object, okay, whereas little r might just be the distance from the center where you want to find the electric field, and therefore that's going to be the radius of your Gaussian surface. Okay, if you want to see that derivation in more detail for inside, it's a repetition of what you saw in example 15, so you can probably go back and look at it. But what you should notice for the relevant bits is that V enclosed is the volume of the Gaussian surface. The other V is the volume of the whole sphere, right? That's why it's the big R. So it's all this volume here, right? All of that. The 4/3 and the pi cancel out. So the right side simplifies to that expression there. You plug in the surface area of a sphere, and you get this result here, or KQR over big R cubed, as you'll see me write in a minute. All right, now, that, again, is something you've done before. What we did here is actually no different from any other Gauss's law problem with spheres that you have done before. It's the same as what you saw in the homework, same as example 15. So the fact that there was this whole like conductor out here changed nothing. Not a thing. All right, now if we go on and let it play until part 2, you're going to actually see the same thing going on when you look at, oh yeah, I guess I have to plug in my answer. There, answer, okay. When we go ahead and do this part, that's outside the inner sphere. Oh, check out my Gaussian surface there. Because of where we're putting the Gaussian surface, the charge enclosed, and because it's a sphere, we can just go ahead and say is Q. We don't need rho or that sort of thing because it's spheres. So the charge enclosed is all of it, because here's my Gaussian surface, there's the charge. I'm enclosing the whole thing. I can actually just call it Q, and no harm done. All right, remember, if you're outside of a sphere, the electric field is KQ over R squared. You ought to know that result so that you know you're going to get that result when you are outside of a sphere. And as you can see, that's what it turns into because of the fact that K is 1 over 4 pi epsilon naught. All right, and then plugging in answers. All right, let's pause for a moment. Again, no different from any other question where I said find the field outside of a sphere, right? Nothing different from what we've ever done before. Now, part 3, when we get to 4r, as you can see, 4r right there is a distance which is inside of this whole object. So what I'm going to write down is the electric field is 0. You should always be able to defend that statement, that the electric field is 0 inside of a conductor. So if you look at my explanation there, right, look at my explanation. The reason the charge, or the field inside of a conductor is always 0 is because, if you recall, right, in my little intro part, I said if the outside surface, or if the inside object here has a charge of Q, the inside surface has to have a charge of minus Q distributed all over it. If that's minus Q, and the other object in here is plus Q, then a Gaussian surface drawn in here encloses a positive Q and a negative Q. That's a grand total of nothing, 0. And therefore the electric field inside the conductor is going to be 0. All right, let's go a little more. Now, the last part, we're going to look at a distance of 6r. And so this is really the only part that's all that new or different from anything that you've had to do before. What you can, let me play it a little more. All right. Oh no, my hand's in the way. Back it up. There. Okay. Now, what you can see from the work here is, when we go out to a distance of 6r, that's outside of both objects. So when I do my Q enclosed, you can see I'm being very careful to include both the insulator and the conductor, right? They're both inside of that circle that I drew. And therefore my Q enclosed is going to be a grand total of 3Q. Two ways you can think about this. Number one, I said in the prompt this thing is Q. I also said the outer conductor has a net charge of 2Q. So if you're out here, the Gaussian surface encloses Q plus 2Q. I think we can add 1 and 2 and come up with 3. The other thing that's actually kind of interesting about how it goes, though, is the total charge is actually always what accumulates on this outer surface. So the inner surface was minus Q. The total charge of the conductor was a grand total of 2Q, which means the outer surface had to be 3Q, because 3 minus 1 is 2. 3Q happens to be the total charge of the system, and therefore that's what we're going to see on the surface. Alright, the rest of this that's going on is plugging in numbers and such, and then we're going to make a graph of electric field. Oh, of course, all of my other scrawlings are in the way. No, that's better. Okay, let's let the video play a little more. This electric field, some parts of it should be not that surprising because it's like what we've looked at before. Okay, so let's concentrate on the bit that's drawn there. The linear part, that's based on this equation. And as we've discussed in class before, the reason it's linear is because of the little r on top there. KQ over big R cubed, those are all constants, and the little r is your variable. So that would be like graphing out, say, y equals 5x, where the 5 would be like the KQ over big R cubed, and the little r is your x. That's a linear equation. Therefore, the electric field increases linearly all the way up to the edge of this sphere. Once you get outside of it, then it follows that other equation that you can't see because it's covered up by my hand, KQ over R squared. Okay, therefore it's going to increase according to, or decrease rather, according to an inverse square. This part is labeled inside the conductor. Between 3R and 5R, that's inside the conductor. So the electric field will drop down to 0 everywhere within that region. Outside of that region, the electric field exists again, right? Remember when we did part 4, we came up with an equation for it, okay, based on the total charge enclosed and those kinds of things. All right, let's let it finish playing, and then you can see what that graph looks like, and that will be the end. Ta-da, done. Okay. If you have any more questions, consult the next video because that one's going to cover cylinders.